covalent bonding with molecular compounds. Be sure to answer the 3 beginning questions. This will help prime you for what you're about to hear involving covalent bonding. So there's 3 types of chemical bonding. We're really going to talk about 2 of those today, may not even talk about the 3rd. So when we talk about the types of bonding, we've mentioned these before. Ionic, which we've talked about already, which is a metal and a nonmetal, while covalent is only the nonmetals. Now, some people might still be confused on where these might be, so I'm going to highlight the nonmetals. So of course we have all of our noble gases. We've got carbon all the way over, phosphorus over, silicon over, and we've got our last 2 here. Those are all of our nonmetals. The metalloids often can portray things like nonmetals, and those have been highlighted there. Really though, the only ones that might come up, silicon, maybe astatine, or arsenic I should say, but really what you're looking at is the nonmetals here. Now, when we're talking about ionic, there's only one type of bond. With covalent, it can either be polar or nonpolar. Now, when it comes to this electronegativity, remember electronegativity is the ability to pull the electrons closer to its own nucleus. So if we were to look at a nonpolar covalent bond, if you have identical atoms, they have the same pull. So there's no one atom that can pull these shared electrons, and that's what this is always just talking about, the shared electrons closer to it. These unshared pairs on the outside here, those belong solely to those individual atoms that they're around, or I should say nucleus that they're around. It's the shared that are contested. But in nonpolar, this happens only between the atoms that are identical. On the other hand, polar comes from this unequal pull. So again, you have your ones that are only chlorines, and then you have the shared pair. One that comes from chlorine in orange, one that comes from hydrogen originally in yellow. This shared pair, as depicted here, is being pulled closer to chlorine because it has a higher electronegativity. Hydrogen has a lower electronegativity. That means this bonding pair, the chlorine is going to be partially negative, the hydrogen is going to be partially positive. That's what that little D looking symbol is. It's partially. Essentially a fraction of 1. It could be 1/4, could be 1/2, could be 1/8. Just think of a fraction, partial. And in this case, this is going to make a big difference to determine a lot of the properties involving covalent compounds. On the other hand, it's a little refresher, ionic. Again, we've talked about this not necessarily happening in every case, but the fact that this big positive and this big negative are attracting. And thinking about their attractive properties, this is a 1 plus, this is a 1 minus. Not a partial charge, but a full charge, which means their attractive forces are much, much higher. Now, some of you might go, well, how do I know electronegativity? Well, we've talked about previously that fluorine is the most electronegative. And that as you move away from fluorine, that electronegativity decreases. So something like sulfur is lower than something like oxygen. And something like carbon is lower than something like chlorine. So some of you might say, well, what happens if you have oxygen or chlorine? I'll try not to put ourselves in that situation where we'd have to look up numbers, just because it's kind of a pain to go through them. So we'll try to keep it simple. But again, the idea is that it's nonpolar if we have the same electronegativity, which we can really only have if we have the same atoms. Different means it's going to be polar. Okay? So keep that in mind as we'll be going forward. It's very important as we go throughout this unit. So, we've talked about ionic compounds and how they bond. Molecular compounds bond differently. Now, the term molecules or molecular compounds is specifically tied with covalent. Much like if you said, my spouse, I know you guys don't have spouses yet, but my spouse implies you're married. It implies that relationship. So when you say molecule, it implies that they are covalently bonded. It can't imply they're ionic, so you don't have an ionic molecule, much like you wouldn't have a single spouse. They would be married. That's the whole concept of being a spouse. Now, let's get back to chemistry. In molecular compounds, the result is that they overlap electron clouds, which means they share electrons. And I can't stress this more enough, but this is the result after bonding. Okay, the result after bonding. Much like if we sidestep and keep on this idea of marriage. You know, people get married for a lot of different reasons, but traditionally, and I'm a traditionalist, the reason you get married is because the positives are more than the negatives. Usually wouldn't marry someone who had more negatives than positives. So the idea is that you guys make a bond because you are attracted to each other for a variety of ways. Positives attracting negatives, just like chemistry. You don't get married to share stuff. The reason people get married is not to share money and share the remote and share TVs and share responsibilities. They don't do that to share stuff. That is a result of getting married, is you share stuff. So, much like we talk about with molecules, the result of this bonding is they share electrons and overlap electron clouds. This is often depicted in this way, to where in red I'll highlight the shared electrons. As you can see, the unshared electrons are around each other atom. Again, shared electrons are depicted between element symbols. Again, another one here. And then they show the dot diagrams, in which dot diagrams, such as circled here and here and here, illustrate how things are bonded, while down here that I'll highlight in green, they use bonds as lines. These are called structural formulas. They show structure. And depending upon your podcasts and what you've seen, you might have seen this a little bit more than others. But the structural formulas show how they're organized and use bonds as lines. When we're doing dot structures, guess what you show? That's right, you show dots, no lines. That'll be reserved for structural formulas, or sometimes called 3D formulas. Up here, we have representations of what are called space-filling diagrams. They kind of show relative sizes of the atoms that are bonded. Now, let's get back to what actually occurs. So a positive nucleus, i.e., I'll highlight in blue, attracts the electron cloud of the other atom. So this is attracted to all of this. Here, 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 and including the electrons that are shared. And likewise, this nucleus attracts the electron cloud over here. And of course, those electrons too. However, think about electrons. Do they want to attract each other? Of course not. So you have the electrons in each pushing each other back. Now, in a successful bond, in a bond that stays bonded, there is positives and negatives, and they come to a balance over time, a short time, in order to maintain a bond until extra energy comes to overcome that attraction and therefore break the bond. A bond doesn't occur when this repelling force is not so small, but actually quite large, to where now the repelling force is bigger than the attractive force. And because that's true, a bond won't happen. So again, I can't reiterate reiterate it enough, the result of covalent bonding is shared electrons and overlapping electron clouds. That's not the cause. Neither is it the stability of the atom to have 8 electrons. Also not the cause. Positives attracting negatives. Higher positives attracting the negatives over the negatives and positives repelling, bond. Otherwise, no bond. Right, so the octet rule. It's a guide to help you determine how things bond, meaning the number of shared electrons, number of unshared electrons. 8 valence electrons puts an ion or atom in a lower energy state, more stable. It's true, but this again is not why they bond. Positives attract negatives. So when we talked about ionic compounds, for something like sodium as an ion, when it loses that extra electron, now it has 8 in its outer energy level and is stable, more than sodium would be. Same would be true with fluorine becoming an ion. Okay? However, something in like water, we have, instead of this losing those electrons, you can see that hydrogen still has its 1 electron and is sharing another electron, in this case with oxygen, when it normally had its 6 and it's sharing 2. Okay? All I see is this is Mickey Mouse, but anyways. So the idea here is that these each retain their own electrons while sharing another electron with another atom. So these are not ions. Ions have lost those electrons or gained those electrons permanently until they don't and either gain or lose them back. But I mean in the sense of after a bond. So that's the main difference. This octet rule will help guide us into determining how many pairs of electrons are shared and how many are unshared. That's where we're going next. Alright, so let's take a look at this beginnings of what's called the electron dot notation. So this shows the valence electrons visually. This enables us to talk about them and work with them on their own. So if we were to use these, we use the symbols. So I'll write those out first. Then I'm going to use blue to increase my thickness here. So when we think about how many valence electrons they have, sodium has 1. Magnesium has 2. Aluminum has 3. Now you might go, why is he separating them? And why is he putting them around there? This helps the notation of these. So this has 4, and you also want to keep them separate until you pair them up again. There's reasoning behind this. This will help you understand how many bonds they're likely to make and will lead you to usually do these things correctly more than incorrectly. But these are all showing the number of valence electrons, as you should remember them from the group number of our periodic table. So take a moment to do it for S&P. Same idea for period 5. Yes, I know some of them will include things like tin, which is metal and ionic and all that kind of stuff, but just follow the same practice and come back and check. So pause and come back and check in a few seconds after you're done. Alright, so here's your answers for each of these. Again, you would only write electrons on the kind of top, left, right, and bottom of the element symbol. No diagonals or anything like that. The idea is that even though these electrons come with these atoms, that doesn't mean that they stay there. What I mean by that is that think of these electrons as like cans of soda you bring to a party. Yes, I said soda, nothing else, just soda. Just because you bring a 6-pack of soda to the party doesn't mean you enjoy all 6 to yourself. Sometimes you might share some. Sometimes you might take other things that people brought. So the whole concept here is that this is how many you start with in total. And essentially, before you determine what makes the compound, everybody puts their stuff on the table. And that'll be kind of a rule as we go through the guidelines of writing what are called Lewis dot structures to illustrate how the bonding actually occurs. So as I've tried to help in this year, I want you to think as little as possible. Following rules, steps, guidelines will get you 90% of the way there most of the time, and maybe you need to think about it every once in a while for the challenging ones. So these are guidelines. Determine the type and number of atoms. So the idea is that, oh look, I have C2H4 as my compound. There is 2 carbons, 4 hydrogens. That's it. Not much there. Total number of valence electrons. Well, I know hydrogen has 4, and hydrogens each have 1, so that means a total of 4. Carbons each have 4, for a total of 8. So that means I'll have 8 for the carbons, plus 4 for the hydrogens, give me a total of 12. Now you want to arrange a skeleton structure. That means using the atoms without any electrons. Least electronegative goes in the center. Carbon is that one. You never have hydrogen or halogens, ever. And you'll connect all by a single bond. So in this case, I'll just kind of do it off to the side. And again, it's okay if you don't understand it right now. But carbons would go in the center. Okay. Hydrogens need to go around. And you could think of, well, I have 4, so can I do this? And the answer would be no, because there's no likelihood of bonding that would say, well, the carbon on the left is going to attract 3 hydrogens, while the carbon on the right is only going to attract 1. That wouldn't make any sense since the carbons are identical. So we wouldn't have the idea of 1 and 3, we'd have 2 and 2. Much more likely that each would attract 2. They're just the same. And we bond these with a pair of shared electrons first. So each of them have that. Now add unshared pairs to each nonmetal except hydrogen, because it only needs 2, so all have 8 electrons around them. So the carbons now have 8. 6 they're sharing, 2 that they're not sharing. Then we count the final number to make sure I use the correct amount. Well, I'm going to highlight this, I think. Let's go with red. And this is the way I always do it to help me not forget. A lot of people want to go around the atom. That's a way to get lost. I just go top to bottom, left to right. So 2, 4, 6, 8, 10, 12, 14. I'm done. 14 electrons in this model. So count the final number, use the correct amount. Hey, oh no, I needed to use 12, not 14. So if I don't have the correct amount, you'll need to use multiple bonds, ones that have more than one shared pair of electrons. So the idea is that hydrogen's only going to want to make 1 bond. So I'll use this information, again, still go with my carbons, still go with 2 hydrogens. Only instead of single bonds between the carbons, I'll try a double bond, because those can make multiple bonds while hydrogens cannot. So then I'll evaluate this again. Does each have 8 electrons around it? Well, I see the carbon, going to use black in this case, has got its 2, 4, 6, 8 around that carbon. The other carbon has its 2, 4, and then the other 4 that it's sharing with the other carbon. Now, does this have 12 electrons? Well, 2, 4, 6, 8, 10, 12. Woohoo! This is my correct here, and I'll kind of redraw it so you can see it a little clearer. as my correct Lewis structure for C2H4. Now some people might go, well, can I put the hydrogens on the top and the sides or the bottom and the sides? And the way I think of this is like a dinner plate, to where if I had on a plate some steak, some potato, and some veggie, that's my plate. My steak is touching my potato, my steak is touching my veggie, my potato is touching my veggie. Everything's in the right spot. Everything is where it kind of needs to be. However, if I turn my dinner plate and I have my steak over here, well, turning that would mean that if I rotated it, I would have my veggie and my potato. Now, is that the same dinner plate? You bet it is. Okay, it's the exact same dinner plate, but just oriented differently. But I still have the same stuff touching the same stuff in the same order. And that's what would be true here. If I did not have the hydrogens on top and I put them on the bottom, I still have carbons double bonded to another carbon and single bonded to two hydrogens. Doesn't matter about that. When we talk about structural formula, that thing will change a little bit. But for here, that's where we're at. Alright, so let's take a look at a few examples here. So, NH3. Hydrogens cannot go in the center, which means nitrogen needs to. Hydrogens around it, doesn't matter exactly where. And now I need 8 electrons. Of course, I need to have them single bonded, and what I mean by 8 is that this has 5 valence, this has 1 each times 3, which means a total of 8 electrons. So I need to at least have single bonds by pairs of electrons, and then the nitrogen currently has 6 electrons around it, 2 more for 8. I match my 8 that I need here. For my hydrogen, I have 2 of them times their 1 valence electrons plus sulfur that has 6 for a total of 8 electrons. Sulfur needs to go in the center. Hydrogens around, again, doesn't really matter where. Single bonded by a pair of electrons. It needs unshared pairs in order to have its 8, the octet rule per se. And that 8 electrons matches my 8 electrons that I've already calculated. Silicon has its 4 valence electrons. Hydrogen has 1 each for 4, total of 8. Not everything will be 8, just in these few examples so far. Silicon has to go in the center because hydrogen cannot, which means hydrogens need to go all around because they only make 1 bond. They can't make a chain or a long line because that would have them bond twice. Single bond all of them with a pair of electrons. And then I see silicon also has 8 electrons, so a total of also 8 electrons. Phosphorus comes with its 5. Fluorine there's 3 of those. They each have 7. So 21 plus 5 is 26 electrons. Halogens cannot go in the center. Phosphorus needs to then, in which it's going to do some bonding with fluorines. Again, they're only going to want to make 1 bond usually. Single bond everything. Phosphorus only has 6. Now it has 8. All other nonmetals need 8. Each of the fluorines currently have 2. Now that fluorine has 8. That fluorine has 8. And that fluorine has 8. Now I need to count up my electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. See how easy that is to count? I've got 26, so that's the correct Lewis structure. Now those are all fine and dandy, but that's not always the case. Sometimes multiple bonds needs to happen. So let's first determine our number of valence electrons for each of these. So 2 times 6 we've got 12 electrons. 2 times 5 gives a total of 10 electrons. 4 plus 2 times 6 there's a total of 16 electrons. Over here we've got 1 and 7 and 2 times 4 for a total of 16 electrons. So all of these need to match these in the end. Now if we look at oxygen and we go oxygen, oxygen, single bond, 8 around each. Oops. 8 around each. How many electrons we've got? 2, 4, 6, 8, 10, 12, 14. Can't do it. That's not 12 electrons. So we go double bond. Two, 4, 6, 8, 10, 12. There we go. And that's the kind of process that we do to where you don't have to think too much about it if it doesn't work. So we repeat the same process with nitrogen. Nitrogen, let's do a single bond, 8 electrons around each. 2, 4, 6, 8, 10, 12, 14. Well, no, that's not going to work. I can just dumbly go, let's try a double bond without actually even thinking anything else. 2, 4, 6, 8, 10, 12. Nope, that's not going to work. Let's try a triple bond. Now each has 8 around it. 2, 4, 6, 8, 10 electrons. And there we go. You can see that takes just a few seconds when you have something as repeated as that. But again, go through the process the same way. If you can approach it the same way, your efficiency and repeatability and accuracy go through the roof, as opposed to you trying to come up to these problems as individual different things. We look at CO2, carbon in the middle, of course, oxygen's on either side. You'll find out symmetry plays a big role. Single bond everything. 8 electrons around it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. No, can't do that. Carbon, oxygen. I can try a double bond with one of them. Now that oxygen has 8. Now this carbon has 8. 2, 4, 6, 8, 10, 12, 14, 16, 18. That's not 16, so nope. And likewise, what I said about the hydrogens fitting around the carbons, it wouldn't go 3 to 1. You wouldn't have a triple bond with one oxygen and a single bond with another. Since they're the same elements 100%, one's not going to favor one over the other. So a double bond with each, in which carbons now has 8 electrons. Now each oxygen will have 8 electrons. Oops, come on, get in there. 2, 4, 6, 8, 10, 12, 14, 16 electrons. There we go. Likewise, we have our C2HCl, carbon in the middle. You could say one hydrogen and one chlorine. Doesn't really matter. They wouldn't have one carbon, would not have both of them though. One of each. Again, let's do single bonds between everything. Each nonmetal needs 8 electrons around it. Hydrogen only needs 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. No. Carbons are going to try a double bond. Chlorine is not going to be likely to make multiple bonds unless put in some very odd situations. But again, it needs 8 valence electrons, as does each of the carbons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Better, but not there yet. So carbon, let's try a triple bond. Two, 4, 6, 8, 10, 12, 14, 16 electrons. And there we go. So there's some for you to try at the bottom. Remember, this 2 negative means something. Think about what it does to your total number of electrons. Draw those out. Come in and be prepared to share. I think I'm going to call some people and have you draw them on the board. See how you did. Come in with your questions and I'll see you soon.